Okay, now everything is organized, we can start. It is my great pleasure to have all of you here. We are arriving to the end of this edition, so we will have now the last session. And the first speaker is Martin Grothaus from Technische Universität Kaiserslautern. So Martin, please, you can start.
Thank you very much for your kind introduction. And furthermore, I would like to thank the organizers for the very kind invitation to this meeting. I'm very happy to be here for various reasons. So I like very much differential equations. I like to construct solutions, analyzing them, but they shall be motivated by problems from physics or more general natural science, biology, industry, engineering. And there's always a problem. They should not be too hard to solve, because then you can't do anything. They should not be too easy, because then it's boring for us. They should be challenging, should lead to new mathematics, and then you solve the problem, and then you're happy, and then you can generalize this stuff. And then you know you generalize in the right direction, because there's a need from nature to solve such problems. And such an example I would like to talk about today. And the first part is a motivation. So my motivation in hypocoercivity and SPDEs was coming from industrial mathematics. And it's about the production of nonwovens. So here are millions of fibers coming down. They are blown by the wind, and then you produce a nonwoven, which you see here on the conveyor belt. So nonwovens are cheap. They are used for single use. They are good filters. And unfortunately, all of us had to use nonwovens 2 years ago, because the FFP2 masks we were wearing, they were made out of nonwovens. So where's the mathematics? So here's a scheme of the production, and there are several parts which can be modeled by math. I'm just focusing on that part, on the Faber laydown. And we have to start very modest. We just start by a single fiber. So what is a differential equation describing the motion of such a fiber? So we have the different forces, and the arc length S is a parameter of the fiber. And then the colleagues from the Fraunhofer Institute in Kaiserslautern, they were modeling a differential equation for this fiber. And it's a second order in time, stochastic partial differential equation of fourth order. We have here a stochastic force, a deterministic force. Here we have the attractive force. What is the challenge? The algebraic constraint. So the fibers are inextensible. That means the arc length should be preserved. That means you know how to compute an arc length of a curve. You just take the derivative, square it, and integrate it. So x is a vector in Rd. So we take the derivative with respect to the space variable, and then the Euclidean norm should be 1. So you need a solution which lives on an infinite dimensional manifold, let's say of a unit sphere in a Sobolev space. And it's already a quite huge challenge to solve this equation. When I was coming to Kaiserslautern 20 years ago, Helmut Neunzeit said me, please solve this equation. And 20 years later, it's still not completely done. So what we could do so far, I mean, we could solve this equation without the algebraic constraint. Then it's not a big problem. This is second order in time. You transform it to first order. It's just a beam equation here, fourth order in time. And then you can add these forces. So it's no problem without the algebraic constraint. The problem is the algebraic constraint. And in a deterministic case, we found a solution together with Nicole Meinecke. We proposed a semi-discrete Euler scheme, and the limit was solving this equation. But to solve the full equation in the case with this term, it's still an open problem. I hope that I don't need further 20 years to solve it. We got now some new ideas using viability theory together with Viorel Babou and Stefan Tappe. And I hope that soon the full problem is solved. But what we did in between? In between, we looked at surrogate models. And this is a very simple surrogate model. We just look here how the Faber lays down on the conveyor belt. So this, we have now two variables. We just take that the derivative is a unit vector, right? This should model this living on the infinite dimensional unit sphere. Now very modest in 2 dimensions. And then you have some force which is acting on the angle. And this is the simplest model for just how the fiber lays down on the conveyor belt. And if you solve this equation, you simulate numerically, you get such a picture. And this, of course, you don't want your FFP2 mask to be, because this would not be a good filter. So to get a good filter, you put on some noise, and then you get such type of an equation. So we here, if in the angle we put some noise, and you already see you get here some kind of a stochastic Hamiltonian system. And if you do numerical simulations, you see without noise, you don't have good ergodic properties. So the time average for large time should be equal to the space average. That is what we are looking for. That would mean that you have a very homogeneous, non-woven, very homogeneous filter. And you see if the noise is getting stronger, we get somehow an optimal mixing, and then it's getting curly somehow. And all of this was done by my colleagues from numerics modeling in Kaiserslautern. And then they came to me and said, this is convergent equilibrium, this is exponential mixing, and there's somewhere an optimal rate. Please prove this for us. And that's such a challenge where I said, yes, that's interesting. And can you solve it or can't you? And it was interesting, because this is a degenerate equation. Here you have noise, which is pushing the system to equilibrium, but here you don't have noise. Like you have with the Langevin equation. It's a stochastic Hamiltonian system. And how to prove that it converges equilibrium. And at that time, when this question was asked, there was Cédric Villani proposed his concept of hypercoercivity. I know my co-author on this project from numerics, he was discussing with Cédric Villani in Oberwolfach, can you apply your method to this equation? And they checked the commutator relations, but they did not fit. So there was no method at that time to show convergent equilibrium. At least we did not know, Villani did not know. What we did, we developed our own method. And this brings me back to particle systems, because at that time I was also studying scaling limits of particle systems. And there was a paper of Ola and Trémollet, which looked at the infinite particle Langevin dynamics and proved in the diffusive scaling that converges to an Ocean-Ulmec process. And there was a nice idea. If you have a generator which has a symmetric and antisymmetric part, you can, you process solve the martingale problem. You can nicely estimate the increments, which are forward-backwards martingales, and Crystal and Stefano could prove convergence of the dynamics. And this idea, I could adapt to this problem, and then we developed our own method, and then we could show that the time average converges to the space average, and you also got rate of convergence. It's 1 over t, or this is the domatic 1 over the square root of t if you take the norm. Sigma was here in the denominator, here in the nominator, there was optimal sigma, and the problem wasn't given by me, by the technomathematics group, was solved. Okay, but this convergence corresponds to exponential convergence to the sigma group, because if we take time average and you integrate out, you get such a rate. But we don't know whether the sigma group really converges exponentially fast. And then comes the game changer, and that was a paper by Dolbeau, Moreau, and Schmeisser. They further developed the concept of hypercoercivity, and this then was also worked on manifolds, and then was my decision. Okay, you should look closer to this hypercoercivity and look how you can apply it to this to such problems. Okay, this was now just motivation. Now you can start over again, if you like. So this is abstractly the problem what we are studying. We have a system of differential equations. The first is just deterministic, the second is stochastic. You can take ODEs, PDEs, SDEs, or manifolds. You just have a product of state spaces, which can be R, a Hilbert space, a manifold, as you like. common is that you have noise in one parameter, not in the other parameter. That is that challenge. And if you have a solution to this equation, and then here, solution of this equation starting in z, you compose this in next function, takes expectation value, you get a function u of t and z, and then you take the time derivative, and then you get the generator of the dynamics. And of course, all of you know about this in all of the talks, or most of the talks where we had Markov processes, we were defining them by the generator. So our starting point is a generator, and we are interested in long time behavior. So we're interested in the law for large times converges to the expectation value with respect to the equilibrium measure. So this function for large time should converge to the expectation value of the function f with respect to the equilibrium measure, or yes, equilibrium measure of the system. And we just now take a functionalistic point of view. We consider the sigma group, which is generated by this operator. By Ito's formula, you can get this operator. You consider the sigma group, and then you check that the sigma group converges to equilibrium with a certain rate of convergence. And then when the problem is solved, later on you construct the process and have statements about solutions of your SDE. That is ideal. Let me give you some examples. So here's the Langeron equations I was mentioning before, which Ola and Tremollet studied with infinite many particles. We consider them now only in the state space Rd times Rd. Then the generator looks like this, Laplacian always corresponds to the Brownian motion. It's a degenerate Laplacian only in V direction, because we only have Brownian motion in the second component. And by Ito's formula, you know how to cook together the generator, and the equilibrium measure is just e to the power kinetic energy minus potential energy minus kinetic energy. We can generalize this. We can take generalized Langeron dynamics or Hamiltonian systems. Then you can have different dimensions in your state space. You have some matrix which is giving the correspondence. And you can take, instead of one potential, you can take two potentials. And here now the invariant measure, the equilibrium measure, is e to the power minus phi 1 minus phi 2. And if in the case if phi 2 is just Euclidean norm, then this would be the Gaussian measure. That would be the special case from before when we had the second order equation. Now we have generalized Hamiltonian system. Further examples are, yes, back to our application from industrial mathematics, where the state space was Rd times S1, right? And we also can do, R2 times S1. And in general, we can also take, of course, consider stochastic differential equations in Rd times Sd minus 1, the units for sphere in Rd. And then we can consider this type of equation. We have now here, this are ID-valued Brownian motion, and this is ID-valued force. This is a projection to the tangent space. And then you write down the corresponding generator by Ito's formula. Here you have a Laplace-Beltrami operator on the sphere, which corresponds to Brownian motion. Such examples we also can treat. And for d equal to 1, it is the problem which was coming from industrial mathematics. And recently we also were interested in infinite dimensional setting, that we have differential operators on infinite dimensional spaces, on real separable Hilbert spaces. The idea is to solve also SPDEs and show hypocoercivity, so exponential convergence equilibrium for SPDEs. So that was the recent challenge which we accepted, and brings us back to the starting problem where we had an SPDE on this infinite dimensional manifold. Okay, that was the motivation. Now the abstract concepts. So on this Langeron equation, many people arbeited. Many people worked. So I already mentioned Villani, which worked on the Langeron equations, and he could show convergence equilibrium in H1 norm for C2 potentials. Then there came the approach by Dolbeau, Moreau, and then Schmeisser. You see, they don't only have a convergence L2 norm, but the framework was more robust for corresponding state spaces. So you also could work with this approach on manifolds. Then also approaches using Lyapunov functions, or you could combine Lyapunov functions and hypercoercivity methods like Kamroth, Herzog, Stolz, Gordiner did, and there are many authors to mention. I'm sure I'm also forgetting some. And then the generalized non-general equation was studied, for example, by Wu already 2001, and he could treat C1 potentials. And then Feng-Yu Wang, he was proving hypercontractivity for the generator, and also could prove exponential convergence to equilibrium. Okay, now our contributions to this problem. In the first mentioned work, together with a former PhD student of mine, Patrick Stilgenbauer, we put these concepts which we learned from Hollin and Tremollet on an abstract level, where we have a generator which is a symmetric and antisymmetric part, and found conditions for convergence equilibrium with this rate 1/t, let's say. And this is using the stochastic process, uses backfed forwards martingales and generalized Dirichlet forms. And the rate is 1/t, right? But the strength of this method is that the potential phi can be very general. So it can be of Lennard-Jones type and only has to be weakly differentiable. You know, in the equation, there's a gradient of phi. So that means the coefficient can even have a jump because we need only weak differentiability. And then together with Patrick, we also transported the ideas, the genius ideas of Loibourg, Moreau, and Schmeisser to the setting of SPDEs, to the Kolmogorov backwards setting, and proposed set of data, also taking domain issues into account in order to apply this stuff to SPDEs. And now the math starts. So far, motivation, history, whatever it is. Now the math is starting. What you have to do? What is the problem? And maybe you in your research of some particle systems have the situation. You have an invariant measure, have a symmetric part, antisymmetric part, and then this approach could help. So we have a Hilbert space, which is just a L2 space respect to a probability measure. Okay. Then we have a generator of a sigma group. You need a nice core. Often these are C affinity function with compact support, or a finitely based function if you're in infinite dimensions. Then we need that L splits up in a symmetric and antisymmetric part, and the domains always should be the core to get the domain issues under control. And on the core, L splits to a symmetric and antisymmetric part. Then we need a projection to the null space of the symmetric part. So, the symmetric part may have a non-trivial null space, and then we add also a projection on the constant functions. Then we need that the measure mu is an invariant measure of L, natural assumption, and the sigma group is conservative. That means 1 is in the domain of L, and L of 1 is equal to is 0. And then something here in addition looks very technically and then abstract. The idea is, instead of Poincaré inequalities, we only need weak Poincaré inequalities. And this function psi here, you should think about, it's a square of a norm, a P norm or an infinity norm. And we here have the L2 norm, and somehow we should put this P norms or L infinity oscillator norm in this setting. So we need a mapping, which is non-negative, maybe infinity, is homogeneous of second order, like a square of a norm is, and it should be on a dense subset, it should be finite, and we need that the sigma group, which we have here, which is generated by L, that it's a contraction with respect to phi. Soon I will introduce another sigma group, this should also be a contraction, and the projection to the null space should also be a contraction with respect to this norm, and then we can formulate the conditions for, I call it, or we call it, together with Feng-Yu, we called it weak hypercoercivity conditions, because compared in comparison with original hypercoercivity conditions of Dolbeau, Moreau, and Schmeisser, we only need a weak Poincaré inequality. So the conditions 1 to 4 are due to Dolbeau, Moreau, and Schmeisser. So, for example, that PAP should be trivial. That's a crucial assumption. But we are more general in the sense that we only need a weak Poincaré inequality. Well, a Poincaré we can only have in the complement of the null space of the symmetric part. So this is a Poincaré inequality for the symmetric part. And if you have this alpha of R is independent of R, then you have just a Poincaré inequality. Because then you can put R to 0 and then you have Poincaré. But we allow that for small r, this alpha of R might go to infinity, is unbounded. And that is only a weak Poincaré inequality. And you will see that this will cover much more examples as a usual Poincaré inequality. And then also we need a weak Poincaré inequality for the antisymmetric part. So an antisymmetric operator cannot fulfill a Poincaré inequality because it's trivial on the diagonal. The right operator, as proposed by Dolbeau and Schmeisser, is this operator. So you take P, antisymmetric part squared, and P, and we need this operator's essential self-adjoint on the same core and also fills this weak Poincaré inequality. And then, well, this is just bounded, some boundedness properties which you need, which you usually follow by hyperelliptic estimates. And then a fifth condition, we should somehow get our norms in this framework, this functional psi. This would actually mean that we need essential M dissipativity in LP or L infinity if this is the LP norm or the L infinity norm. But we found a weaker condition, which is easy to check in applications. And this shows that the core we have, the core of L is also nice for the other norms. Okay, that are all the technical assumptions. And if we do those assumptions, then we get the following result. If we have our data assumptions, weak hypercoercivity 1 to 5, then we get the sigma group converges to its expectation value of f with a rate psi of t. Here we have a constant just depending on f, on the L2 norm of f, and maybe the LP norm of f, and this is the rate. And the rate is given quite explicitly. Here, this beta and alpha are the functions from the weak Poincaré inequalities. Okay, they give the rate of convergence. Looks at the moment quite abstract and maybe not useful. I will compute soon for you these rates. Okay, this result I obtained together with Feng Yu a few years ago. Okay, if you then have this result, so far we don't need any probability. But of course, you would like to interpret this for SDEs or SPDEs, and then you use potential analysis or generalized directive form, construct the corresponding process, and then you have statements, ergodicity statements for the corresponding process. Okay, now let's see if it's applicable, what we did. I mean, we have all these assumptions. Is it applicable? What are the rates of convergence we are getting? What are the rates? Okay. Back to the generalized Hamiltonian system. Is it applicable? Okay, the invariant measure we already have. Then we can decompose L in a symmetric and antisymmetric part. So this here is the symmetric part. You see that if you have here not this sigma, then you just have here an Ornstein-Uhlenbeck operator. And here you have the antisymmetric part. And what we have to check a Poincaré inequality, but if you have C2 potentials, then you always have a Poincaré inequality, a weak Poincaré inequality. In order to have a Poincaré inequality, if you have a density which is e to the power minus a potential, then the potential should diverge in a linear way to have Poincaré. Sublinear, you have only weak Poincaré, but for weak Poincaré, you only need that the density with respect to the Lebesgue measure is locally bounded. So, of course, if you have e to the power minus phi and phi is C2, of course it's locally bounded. So, trivially, you have a weak Poincaré inequality. So, it's about tails. You can have very slow convergence. I mean, you can to treat distributions like the Cauchy distribution or something like this. So you have, the density can very slow go to infinity for large x, and still you have weak Poincaré inequalities. Then we need this kind of estimates that we need in order to show essential M dissipativity, that D is a core, and right. And then, of course, if we have here a second potential, the second potential should not deviate too much from the Gaussian setting. This is fixed with this condition, which one has to check, and then it's applicable. Examples. We have two potentials now. Yeah? Remember, the invariant measure was e to the power minus phi 1 minus phi 2 of x and y, dx dy, so density with respect to the back measure. Let us take for a moment some polynomial divergence of the potential. So phi 1, phi 2 is up to a bounded C2 function given in this way. Then the critical situation is delta and epsilon equal to 1, because then we have linear divergence. And then one has Poincaré. So we would expect we should have an exponential rate of convergence, and that's true. If epsilon delta both are 1, here we get 1, and this here is 0, and this here is 0. 1 times 1 is 1. So for if we have a Poincaré inequality, if we have a linear divergence, then we can reproduce the well-known hypercoercivity results that we have exponential convergence. But what happens if we have a slower decay to infinity? For example, if you have that one potential is going like the logarithm. You know, you have e to the power minus this potential. That means this dimension 1 would correspond to the Cauchy distribution. Then we still can explicitly calculate the rate of convergence, but of course it's no longer exponential. You have here some logarithmic, and you have here some 1 over t convergence, but still explicit. And even we can have that both terms decay very slowly. Now let me grade the potentials, and in both components, let's say you have the Cauchy distribution in dimension 1, and still you get convergence rates. So then in this situation, the classical method of hypercoercivity would fail, because you always need a Poincaré. In this situation, you don't have a Poincaré, but we still get convergence rates. Okay, then maybe finally about the infinite dimension setting, I started 5 minutes late.
4 minutes.
4 minutes.
5 minutes.
Yeah, okay. What was then the progress in infinite dimensions? First, we also now can treat multiplicative noise. That means in the Laplacian, you have some coefficient now. And for application in physics, multiplicative noise is very important. Then we can add here in the SPDEs, we can add a nonlinear term, the gradient of a potential. And if we put here B1 equal to A2, we just have an identity. We have a second order equation. And in general, we have that the operators Q, that they are symmetric operators which diagonalize. That is a setting which we now can treat in order to treat SPDEs. I think I cannot go so much in detail. So the assumptions are, I mean, what you need? You need somehow that this operator valued function is Fréchet differentiable, and then you need certain assumptions on the Fréchet derivative. And maybe I should not be so technical at this point at the end of the talk. I mean, this is the invariant measure. Now, as invariant measure, we take the product of two Gaussian measures with e to the power minus phi, the potential, which might be non-quadratic. That means we have non-quadratic situations. And final example, the stochastic Cahn-Hilbert equation, which we can treat. So then the Hilbert space is a dual space of a sublet space 1, 2, where function of expectation value is 0. And the operator Q is an inverse of the fourth derivative. The fourth derivative is typical for Cahn-Hilbert equations. Then we can allow multiplicative noise, which really depends on all dimensions. So it's not only that we have that finite modes are active. And potentials in this setting are usually introduced in this way. You take a C1 function, then you integrate it, and if you take such potentials and really taking the derivative means you get polynomials of your process, so you get a nonlinear processes which you can treat, and this is then the final result. So we can have a solution to this nonlinear Cahn-Hilbert type equation, which can be considered as a second order Cahn-Hilbert equation if we put here equal to 1. And then depending on the coefficients, the minimal which we have is essential M-dissipativity of the operator, then we have corresponding sigma group, and we have the process exists as a right process giving martingale solutions. If you restrict our coefficients more, we have a weak diffusion process and weak solutions. And if we have the parameters in this range, we have hypercoercivity. That means that this process exponentially fast converges to equilibrium. This was obtained together with my PhD student Alexander Bertram and Benedict Eisenhut, and that's what we did during the pandemics. Together, before the pandemics with Feng Yu, we generalized everything to weak Poincaré inequalities. Together with Maximilian, we put the concept on manifolds to treat the problem from industrial mathematics. Together with Alexander, we could treat the case with multiplicative noise, and here with weak Poincaré multiplicative noise, and together with Benedict, we treated the SPDEs. Thanks a lot for your attention.
Thank you, Martin. It's nice to see that the industry is doing a good job based in the...
It's motivating us.
Yes. Any question, please? Yes.
Dolbeau, Moore, and Schmeisser, they believe that their strategy is limited to problems with hypocoercivity index 1. Do you think that exchanging Poincaré by weak Poincaré will alleviate or help in this direction?
That's interesting. I haven't thought about it. I will think about it. That could be. I will think about it. It's an interesting question. I haven't thought about it. I will. Thank you. Yeah.
So,
sorry.
As far as I know, so when you have like the symmetric part, usually the symmetric part is only like well behaved, that it is coercive in some sense.
Yeah.
With some in some small space, so you put some weight. So I know it for linear also, you put like a
Right.
weight. So is this also the case?
Yes, it's also the case here. We assume a weak Poincaré inequality in the complement of its null space. And on its null space, we have then the antisymmetric operator. And there we consider the operator PAAP. A is antisymmetric, and that also fulfills the weak Poincaré inequality. So there where, in the null space of symmetric part, where we don't get help now pushed into equilibrium, the antisymmetric part helps. So that means the components are mixed. But we see this by having this operator PAAP in the null space of symmetric part. And then we get, from this operator, we get Poincaré, weak Poincaré, and the push to equilibrium.
So you need to restrict yourself to this smaller space usually.
Right. The symmetric part I reduce to the smaller space, right? And then I have the product structure. And then in the complement, I have another operator which helps. And then you have it at the end in the full space.
Okay. So the total theorem is without restriction to...
Right. Yes, it's in the full space. Yes. It's in the L2 on the product space. Right, it's not full space. Because and one component, the symmetric part helps, and the other component, this PAAP, helps. That means the components are mixed. But we have it on the full space, right?
So the symmetric part does not need to... Because I know some like these enlargement theorems that I don't know, probably they were proved before, but Moore had like these kind of things, and he called them like factorizations for non-symmetric operators or something like this. And there he needed like that this symmetric operator splits into like a regularizing part and a strongly coercive part in a larger space. And I was wondering if this is also the case here, but apparently not.
That sounds like vice versa. But we don't have to restrict ourselves to a subspace. I mean, convergence really have in the full space. And what you said looks like the vice versa idea.
Okay.
Both on the fiber equation and on your equation, you have a first order derivative.
Yeah.
Why is that so? What is the physical meaning?
The physical meaning is the colleagues from technomathematics were modeling this, and they were using the Korsarot-Rod theory. Korsarot-Rod theory. That's also a theory which you use for liquids, and if you're studying beam equation and such fibers, you use a Korsarot-Rod theory. And then they were modeling this equation and then this fourth order term showed up. They also combined some equations, plugged them in each another, and then they end up with this. This is also typical, without this force, it's also called the beam equation. That is used in order to describe beams. But the physical, if you're interested to read in the physical background, I should go back to the derivation. That was done 20 years ago, I don't remember.
It's a bit strange because it's not a diffusion.
Yeah, it's second order in time also, right?
Okay.
Okay, Stefan?
You try to use the tropic hypercoercivity, which is better control of the dimension.
In order to do SPDEs.
Yeah.
So far not, so far not.
But somehow we use the tropic.
Yeah, right.
And it gives you control in the dimension of the system. So it works very well for the infinite dimension.
Yeah, I mean, our stuff also works for the infinite dimensional, in the infinite dimensional setting, so we can treat SPDEs. I mean, the last example was also in Hilbert spaces. It works. But you're right, it might work even better if we use this method. So I should compare whether we can get further there. But our result is already in infinite dimension. So the SPDE, there's a state space is then the dual space of a Sobolev space.
Okay.
I mean, then you have full control because it's infinite dimension of the dimension, because it's infinite dimensional.
Infinite dimension.
Yes, right. It's infinite dimensional. So here, in this setting, we had the state space U was a dual space of the Sobolev space. So it's an infinite dimensional setting. And that is why we can treat such type of SPDEs. For this, we need an infinite dimensional space. So this was the abstract setting. That was the abstract setting. So we have this equation, which takes value in U times U, where U is a separable Hilbert space.
Martin, may I suggest that we interrupt the discussion?
Sorry.
And perhaps we can continue. No, it's interesting.
Yeah,
At the same time, we are very constrained to.
Yeah.
So if you have more questions, we can continue in the next edition, because following the suggestion by Stefan, we have to arrive until 55 editions or even more. Okay, thank you.